G'day guys, welcome to video 5 of topic 1 of unit 3, Latent Heat. This video will be covering the main ideas of chapter 2.4 of book 1. You should complete this reading before class. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the knowledge and skills table. Alright, so down here we can see we need to be explaining this term and we have a definition here. So our first knowledge is going to be, well, what is latent heat capacity? We need to know what these words mean. Second thing we need to know, well, what is a phase change? Because we're asking here to calculate the energy of a phase change. If we don't know what it is, we can't really calculate with it. And finally, under the skills, well, can we actually calculate that energy? Because we're going to apply that numeracy to these things. Now, I am recording this a little bit in the future, but hopefully by the time you watch this video, we would have recently done a lab where I've demonstrated to you heating ice from around about -4 degrees all the way through to boiling. The graph probably would end up looking a bit like this. So if we have our y-axis here, that would be temperature, ranging from about 100, there'd be a 0 line, and the ice is about -4 coming out of the freezer. So let's just draw our horizontal x-axis for time there. It probably would have been something like, well, little bits, and then slowly, and then starts to slowly increase, rapidly increase. Oops, went a bit too far there. This one doesn't have an eraser on it. Eraser. Let's just erase a bit of that there. I do it in a small section, so yeah, roughly 4 degrees for a bit, starts to heat up, kind of slowly goes up, then goes up fairly quickly for a while, and then plateaus off for a bit. We would have seen a fair amount of messiness for it. There might have been a few dips up and down because as the ice kind of settles in, it spreads out that cold, or it absorbs some of the heat out of the hot water, or the hotter water I should say, to help melt the ice, and the temperature fluctuates a bit. Eventually it all becomes water and then slowly goes up, and then it levels off like we would have seen in our first mandatory prac at this unit. Now this is called a phase change diagram. Okay, as it shows the temperature of a substance changing between two different phases over time. In this case, we saw our solid phase, we had to change, then we saw our liquid phase, and then finally we start to see our change into a gas there, though with that temperature sensor we can't measure the temperature of the graph. In the textbook, this is more like what a phase change diagram looks like. I'm going to give you a few reminders of theory that we've discussed in class, and then I want you to try to give a go about why there's a discrepancy here. So remember, the temperature of a substance is the average temperature. Some particles will be hotter, some will be colder. The heat from the Bunsen burner is applied to the bottom of the beaker. Could have been a hot plate, haven't done the prac yet. And finally, heat takes time to move through a substance. Okay? So pause the video for a second, taking those three into mind. Temperature is an average, means some are hotter, some are colder. We put the heat at the bottom, and it takes time for heat to move through a substance. Why did we get something more like this compared to this? Where we can see here, gets to 0, stays 0, gets to 100, stays 100, before continuing on. So give it a pause, and then we'll wait. Okay. Now you may be this could be a little bit tricky to start off with, because we give you a lot of these nice, neat, pretty graphs when it comes to theory and science, but then in real life things look very different. What this is sort of considering here is that all the particles are heating up evenly, and they all hit 0 degrees Celsius at the same time, and then they all phase change and they all turn into water at the same time, and they all heat up. It's them all doing the same thing, and that's just not true. As we said from that first principle, that it's the average temperature, not everything's temperature. So some will be water, while some will still be ice. Some will phase change before others. There's no way to control that. And the reason this happens is because of those other 2 points. We apply heat to the bottom of the Bunsen burner, so it makes sense that the bits at the bottom would turn to ice first. Turn from ice to water first. And so the ones at the top would take longer before they start to heat up. That's why convection currents exist, because the ones at the top are colder than the ones at the bottom, and we end up with a rotational circuit as the energy transfers through the substance. So whenever you are comparing a ideal graph against what you actually have, and that can be really important whenever you're doing a data test on those sort of things, you need to consider, well, what is my limitations of my model here, or what about for my experiment? Are there things that I need to consider with how I'm doing this, so that you can actually identify your limitations, suggest improvements in order to try to make it as close to ideal as possible. We'll never get perfect, however, it will end up being hopefully better, or at least more usable for you. Okay, now when we started this unit, we talked about energy stored between atoms in bonds as potential energy, and how different different states of matter have different amounts of bonds. We have solids with tight bonds, all the way through to gases with extremely weak to nearly no bonds between the molecules, and then liquids in the middle. Now, if you're going to overcome bond energy, you have to give something energy, and that's what we call latent heat. It is the energy required to overcome bonds and cause a phase change. Sometimes this is called latent heat capacity. Some texts will just call it latent heat. Now, here's the annoying part of this, and honestly, I don't get too hung up on thinking about these, but I can pretty much guarantee that these would be the sort of targets for an external test where they want you to use the specific jargon. So the 4 words, they go with the different types of phase change. Now, latent heat of melting is for a solid turning into a liquid, because that's what we call it, melts. Think about ice, ice melts. But when we call water going back into a solid, sometimes this will be called freezing. More often they will be called fusion, because freezing is more thought about for ice, because it's becoming cold. But you could have say steel fusing at 800 degrees Celsius. I think the melting point for steel is like 900 or so, something. Might be a bit higher, but that's pretty hot to us, but that would still be the temperature that it goes through fusion at. So we've got melting for a solid becoming a liquid, and we've got fusion for liquids becoming a solid. And we generally use whatever word matches something at room temperature. Even though it means the same thing, you'll see water listed as the latent heat of fusion inside the equation booklet, because water is a liquid at room temperature, and so it fuses or freezes to become ice. However, you may see for metals it referred to as the latent heat of melting, because metals are solid at room temperature. Now the other pair is for the gas-liquid phase, and you'll have latent heat of vaporization, think of evaporation, so vaporization for a liquid turning into a gas, and the opposite is condensation, the latent heat of condensation to go from a gas back to a liquid. Now, what's really important for you to remember is that a phase change involves energy, and so when a solid becomes a liquid, and then a liquid becomes a gas, we have to give something energy. So if you think about ice, if you have a lump of ice there, you give it some energy, and then it turns into water. You take that water, you give it some energy, it becomes a gas. Okay? But the other way, we've got to take energy away. So whenever you're doing these ones will produce a positive value, or these ones should produce a negative value, because for these ones we need to give something energy, these ones we need to take energy away. Okay, so that's an important point to remember there. The formula for this is pretty straightforward. Q equals ml. Okay? Q is an energy change, a heat change. So we're using the same thing as with our specific heat capacity formula that we saw in our last video. M is our mass in kilograms, and L is the constant for that phase change. Now, the phase change for solid to liquid and the energy for a phase change from liquid to solid, they are not the same. Okay? They will have different latent heats. While liquid to gas and gas to liquid, so solid to liquid, liquid to gas, I should be going this way, they are very different things. While solid to liquid, liquid to solid, these ones will have the same size, the same magnitude, but they will go in different directions. Okay? So, what I want you to do for an activity now is I want you to draw a graph like the one you saw earlier in the video. Feel free to rewind if you want to take another look at it. And I want you to label those different sections with their appropriate formula. With the constants, so the C's and the L's, make sure you specify what the name of that constant is. Don't just write CLL in it and not identify what it's called, because this will give you a good visual reminder of what it is. So y-axis should be temperature, x-axis should be time or energy. Often you'll get both in data tests or on your external exam, where they'll either show you how it changes over time, or it'll show you how it's changing with response to how much energy is being given to it. Each of the slope sections, the heating phase, is going to obviously use our Q equals MCAT formula, while all the flat sections where we have a phase change, and there should only be two phase changes, we'll use our Q equals ML. Then make sure you write what those L's are. Give that a go, and then come back to the video, please. Okay, so hopefully you gave that a shot. It's certainly a good way to help you remember where different formulas get applied. I use a lot of visual representations for my study book, or my little personal journal I have for my physics notes, where I will then draw pictures and diagrams and label the relevant equations to help me see connections and things like that. Let's do a couple of examples now. This is example 2.4a from your textbook. How much energy is required to change a 2 kilogram block of lead to liquid at its melting point? So lead is obviously a solid in our day-to-day life, and we need to turn it from a solid into a liquid. Note, there's nothing here about what temperature it's at. We're only caring about the phase change here. But we will need some information about lead. The good thing is, you're not expected to memorize any of these constants about specific heat capacities or latent heat capacities. They will always be provided to you on your text. The water ones are actually in the constants in your equation book. If they wanted you to work with steel, they'd have to give it to you on the question, for example. They might ask you to work it out for steel. However, they'd have to give you all the other values that you'd need. So, on, I believe, either the same page as the worked example or the previous page, there is a table that has substance, latent heat of fusion, and latent heat of vaporization. So in here, they've only given us what it is to freeze and what it is to turn into a gas. However, as I said on the previous slide, that this thing here for fusion is also the same energy it takes to melt it. This just tells us this is the energy that it would give off turning into a solid, and all we're going to do is flip the direction of it to go, well, this is how much it would take to melt it. So, there's my pen. We're after an energy, that's a Q. Q equals, I don't know. We have a mass, 2 kilograms. And because we're dealing with a phase change, we need the latent heat capacity. And so in this case, we're going to need this one here on the left because we're melting it. And melting is the opposite of fusion, 2.30 times 10 to the power of 4. I will actually just change that mass quickly, because the text has given us that it is 0.200 kilograms to 3 decimal points. Sorry, to 3 significant figures, not 3 decimal points. And that way we can see, well, these both have 3 sig figs, so our answer can have 3 sig figs as well. Note here, this number would be very big and very different. If this was a multiple choice question, using the wrong latent heat would be a valid distractor and something that you would probably see happening. So, let's plug that into the formula. Q equals ml equals 2 times 2.3 times 10 to the 4, and that's going to be 4.60 times 10 to the 4 joules, because it is an energy. That's it. That's easy. Nice simple formula. Let's have a look at another one. An ice tray containing 200 grams of water at 25 degrees Celsius is placed in the freezer. How much heat energy has to be removed to change the water into ice at -4 degrees Celsius? Now, we do have to use some of the stuff we had from our previous topic on specific heat capacity, and they've been nice enough to give us the specific heat capacities for water and ice. It is important to remember different phases will have different specific heat capacities. We're also going to need this. We're going to need the latent heat for water, and here we have the latent heat of fusion. We can see the latent heat of vaporization is about nearly 10 times bigger, and that is not the number we want. So let's think about this. We're at 25 degrees, so I'm just going to write out the temperatures for a second. We're at 25 degrees Celsius. It'll cool down to 0 degrees Celsius. It will then freeze, and then it will cool down to -4 degrees Celsius. So this section here, we're going to need a Q equals mc delta T, because we've got a temperature change. This section here, we're going to need a Q equals mc delta T for that temperature change, 0 to -4. And the freezing here in the middle, we're going to need a Q equals ml. And when we take all those, we can add them all together. And that will be the total amount of energy removed in order to work out in order to freeze this water. Let's write down our values. We have mass equals 0.2 kilograms, because it's 200 grams. Always convert to your SI units. For this one here, I'm going to call this delta T1. I'll call this delta T2. Delta T1 equals -25 from 25 to 0. Delta T2 equals -4 from 0 down to -4. We'll call this C1 and C2. C1 equals 4180. C2 equals 2050. Now, when we've got our latent heat, pardon me, had to sneeze. Latent heat of fusion is this number here, 3.34 times 10 to the power of 5. And you notice here the constants, even though we have a big temperature change here, 25 degrees is not huge, but it's a good chunk. These constants are so much smaller than these ones. So a lot of the energy that it takes for making things cold or frozen goes into the actual freezing process, not the cooling down process. There are a couple of ways that you can actually do this working out. You could write them all out in one line. You can even factorize out the m out to the front, because it's going to be the same m in each of them. Add all these other values up and then multiply it at the end. I'm just going to work out each bit one at a time. So this first bit up here, we have 0.2 times 4180 times -25. I'll grab a calculator. 0.2 times 4180 times -25 gives us -20.9 joules. Oh, no, sorry, that is a comma then, not a decimal. It's a little bit dark in my office tonight. 20,900 joules. Okay, I'm going to do the second, so there's our first temperature. Our second temperature, I'm going to do the same thing, 0.2, but this time 2050 times -4. This one will be a bit smaller. 0.2 times 2050 times -4 gives us 164 equals -1640 joules. Now let's do our last one. Q equals ml. 0.2 times 3.34 times 10 to the 5. And that's going to give us 6.68 times 10 to the 4. It'll be a negative number because we're going to remove the heat. Okay, so this is our phase change. Okay, this is our two cooling periods, and you can see here, even though that's 20,000, I mean that's what 10 to the 4, so that will affect this, but that bit here was 3 times larger than this bit up here. Okay. So now let's add those all together. 6, 8, 10 to the power of 4 plus 2900. I did just say plus because I'm just ignoring the negatives for the moment. Plus 1640. So we get a final energy, Q equals negative 89,340 joules. Now, sometimes I will then rewrite this as a sentence. It's very good with energy type questions to kind of do that, just to hedge your bets, unless there is only a calculate or a determine box where you need to write your answer. If you write a sentence saying the energy removed was 89,340 joules, it allows you to be really clear about what you've worked out. But writing it as a negative will also be acceptable to say, yes, this is energy change, or negative energy change. This is energy that's been taken out of a system. All right. 2.4c. A beaker contains 150 ml of water at the boiling point. What extra thermal energy is required to vaporize it at 100 degrees Celsius? So they're saying it's already at 100. What's required to turn all of this into steam? Again, let's get those numbers we're going to need. Here's our water table again. This one's a little bit easier. We don't have a mass, we have a volume given to us, but remember 1,000 milliliters of water is the same as 1 kilogram. So this will just be 0.15 kilograms. We have a latent heat of 2.26 times 10 to the 6. So because we're after vaporizing, they sometimes will phrase this as boil it all to steam or convert it all to steam, something like that, where we're changing the phase. But we're going to need the latent heat of vaporization over here. We're just going to slap our values together. Q equals ml, 0.15 times 2.26 times 10 to the 6, and that's going to be about 3.4 times 10 to the 5. 2.26 10 to the power of 6 times 0.15, so 3.39 equals 3.39 times 10 to the 5 joules. Right. That one was a bit easier. The only trick here was working out the mass and making sure we're reading the correct column from our tables there. Alright, so in this video we have done the following. We've compared theory to practical data, we've defined and explained the concept of latent heat, and we've calculated the energy required to phase change a substance. For your entrance slip to class, please complete questions 1 to 3 in chapters 2.4. check your learning PDAs and copy your answers into the 3.1.5 space on eLearn. I know, only 3 questions, it's not a typo. That's all you need to do for this chapter. Have a good one, and I'll see you next time. Thanks, guys.